Okay, today we're going to learn another method for finding the force of gravity. So, up to this point in physics, we have learned how to calculate the force of gravity. For example, if we had this situation, so there's a box sitting on the floor. When we drew the free body diagram, we learned how to calculate the force of gravity. It's equal to mg. Okay, so there's one way of calculating the force of gravity. But this method of calculating the force of gravity only works on Earth because g, which is the acceleration due to gravity, has a value that's specific for Earth, 9.8 meters per second squared. But if you were to leave Earth, this value is going to change. So today we're going to learn another way of finding force of gravity that will work anywhere in the universe. Okay, it works anywhere in the universe. Here's the equation that we're going to learn. So force of gravity is equal to g times m1 times m2 over d squared. This equation is known as Newton's law of universal gravitation. And it works, like I said, to find the force of gravity anywhere in the universe. So if you've got the mass of one object and you have the mass of the other object, and you know the distance between those two objects, there's a gravitational field between them, and we can figure out the force that is there. And so again, just another way of learning how to calculate the force of gravity, as long as we know the mass of the object, number one, the mass of the object, number two, and the distance between them. Okay? And so let's get started, and we'll show you how this works. Okay, so let's look at this equation and try to figure out what it means. Hopefully you're following along in your guided notes. There's a spot for you to write this equation. So Newton's universal law of gravity. Okay, you're supposed to write down this whole equation here. And we're going to talk about it for a second. Okay, so F sub g means force of gravity. So the force of gravity between these two objects is equal to big G. Now this is a new value we haven't talked about yet, so let me explain it. Big G is the universal gravitational constant. So it's a constant. It will always be the same number, and I will always provide you with that number. Its magnitude, so big G equals this number, 6.67 times 10 to the minus 11. So it's a very small number. We move the decimal 11 times to the left. That's what that constant magnitude would be. But I want you to pay attention to its units. The units of G are Newton meters squared per kilogram squared. So when we take the distance between these two objects, we're going to do it in meters. When we find the mass of the two objects, they've got to be in kilograms. So this will only work if we're taking the distance in meters and the mass in kilograms. Okay, m1 is the mass of the first object. m2, right here, is equal to the mass of the second object. All of that is divided by d squared here. So d is the distance between those two objects, and it's the distance between the center of the objects. So if we're talking about two planets, we're going to go from the center of the objects, and then that's what we're going to measure as the distance. And then remember, always remember, you got to square the distance. So there's this inverse square law happening in this equation. So, okay, there's just an overview of using Newton's universal law of gravitation. Let's see how we'll actually use it though. Okay, so practice problem number 4. Let's go through it together. It says proportional reasoning with gravitation. So we can reason through this problem and use proportions to do that. It says if you double the mass of one of the objects, how does the gravitational force change? And so here's our equation. Okay, what if we were to double one of these masses? So it doesn't matter, either m1 or m2. What if we doubled it? Well, let's just see how that would change. We would still have g. That's going to be the same. It's a constant. But now we have 2 times m1. And we still have m2, and it's still going to be the same mass. And it's still the same distance between them. And so really, if you were to solve this equation, it's going to be, the force of gravity is going to equal 2 times what it was before. So force of gravity is equal to 2 times whatever it was before, because we've times the mass of this one by 2. So the answer to this practice problem is 2 times. So if you double the mass of one of the objects, how does the force of gravity change? Well, it doubles. For example, if you had 2 planets, let's say, I don't know, you have planet A and planet B. Well, there's a force of gravity between them. Okay, let's look at how that would change if A stayed the same size, but B doubles in size. Well, now, if this was 100 newtons between them, now the force of gravity, if we kept the distance the same, but all we did was this one's 2 times the mass, so now the force of gravity between them is going to be 200 newtons. We just kind of use proportions to figure that out. So hopefully that makes sense. Okay, so let's go to the next problem and see if we can't get the hang of this. So practice problem number 5, it says, if you double the distance between the 2 objects, how does the gravitational force change? Again, we're going to use Newton's law, universal law of gravity, right here, and kind of use proportional reasoning to figure this out. Okay? And so it doesn't look like we're changing m1 or m2. They're staying the same. So when we look at this, force of gravity is equal to big G, which is the gravitational constant. m1 staying the same, m2 staying the same, but the distance between them is doubling. So what are we going to put in for D? Well, we're going to put in 2 because it doubled the distance, but we can't forget to square it. And so if you solve that, everything's going to be the same on top, so I'm just going to call it 1. And on the bottom now, because we're taking double the distance, so 2 squared is 4. So now the force of gravity is equal to 1/4 whatever it was before. So 1/4 as much. Okay, that's your answer to practice problem number 5. Okay, so let me see if I can draw that. If here's planet A and here's planet B, okay, we're not changing their mass, but we are doubling the distance between them now. So if this was 100 newtons of the force of gravity between them, now let's see if I can draw them at the same mass. So this is A, it's supposed to be the same size here. But now B is twice as far away, so I'm going to come over here and it's still going to be the same mass. So the force of gravity between these two would be 1/4 as much as it was before, so this would be 25 newtons. Okay, and that should make sense from what we did with the inverse square law, because that's all that's happening here is we're taking the square of the distance between them, and now it's going to be 1/4 as much. So anyway, the answer to that was 1/4 as much. Okay, I know that this stuff is a little bit complicated, but when you get the hang of it, it's really not. So I've got some extra practice problems. These are not in your guided notes, but I would like you to think about it and write down the answer in the margins of your notes. Okay, so let's do extra practice number 1 for this. It says, by what factor would the gravity change if you doubled the mass of both objects and doubled the distance between them? Okay, so we're doubling the mass of both of the objects, but we're also doubling the distance between them now. So let's use this formula again. Force of gravity is equal, G is not changing, but now we're taking twice the mass of m1, and we're going to double the mass of m2 as well. And the distance is also doubling, so we got to remember to square that. Okay, so what I did is I just put a 2 in for m1, a 2 times m2, and we're timesing the distance by 2 as well. So here's how you figure this out. Force of gravity is going to be, you just times these top 2 together. So 2 times 2 is 4. So whatever it was before, now because you doubled the mass of both of them, that's 4 times as much gravity between them. But we also changed the distance between them by double, and so 2 squared is 4. So 4 goes on the bottom as well, so 4 over 4 is 1. So you changed the factor of the force of gravity by 1, which means you didn't change it at all. Actually, it was just a wash, okay? Even though you doubled the mass of both of them, because you moved them twice as far away, it equalizes each other. And so now whatever the force of gravity was before, it's still the same. So I would put no change. Okay. So let me see if I can illustrate that with planet A again and planet B. Okay. And so A is getting twice as massive, so let me see if I can draw about twice as big. And B is getting twice as massive, but they're doubling the distance between them. And so even though B got twice as massive, if this force of gravity here was 100 newtons, what would the force of gravity be between these two planets? Well, because it didn't change by a factor of 1, it's still the same. So this would be 100 newtons. Okay. All right, let's do extra practice problem number 2. It says, by what factor would the force of gravity change if you doubled the mass of one of the objects and quadrupled the mass of the second object and tripled the distance between them? Okay. Again, I'm going to write down force of gravity. G is not changing. That always stays the same. It's a constant. But it says we're doubling the mass of one of them. So I'm going to take m1 and times it by 2. Okay, and we're quadrupling the mass of the second object. So quadruple means times it by 4. And then it said we're tripling the distance between them. So what are we going to put in for D? Well, that's 3 because we tripled it. But you still got to square it. So when you calculate that proportionally, force of gravity is going to change by this proportion. 2 times 4, which is 8. So I just did 2 times 4 because we doubled the mass and quadrupled the mass. So that's going to change the force of gravity by 8, just doing that. But because we tripled the distance between it, 3 squared is equal to 9. Okay, and so the force of gravity is going to change by a factor of 8 over 9. And if you put that into a decimal form, 8 divided by 9, the force of gravity is going to change by a factor of 0.89. So 0.89 times as much. Okay, so that would be my answer for this one. And so, yeah, if it was 100 newtons before, so if this was 100, now if you doubled the mass and quadrupled the mass and tripled the distance between them, so now there's a lot more distance between them, you would take 100 and times it by 0.89, and now there would be 98 newtons of the force of gravity between them. All right, let's do one more practice problem like this. I think we're kind of getting the hang of it by now. It says, by what factor would the force of gravity change if you half the mass of the first object, tripled the mass of the second object, and decreased the distance between them by half? Okay. The universal gravity constant is not changing. The first one, we took half the mass. So I'm going to times that by 1/2. Okay, and the second one, we tripled the mass. So I'm going to times it by 3. And what did we do to the distance? We decreased the distance between them by half. So in for D, I'm going to put in 1/2, but we've got to square it. So let's see proportionally how that changes the force of gravity between these two objects. So I would take 1/2 and times it by 3, and then you've got to do the square of the 1/2 underneath. Okay. So here's how I would figure that out. So on top, just by changing the masses, that's 1.5 times the amount of gravity. So it did increase the gravity by changing the masses. And then we've got to calculate how this changes it, the distance. So 1 squared is 1, and 2 squared is 4, so that's 1/4 on the bottom. And 1.5 divided by 1/4, let's see what that is. So that's the same thing as 1.5 times 4, which would be 6. So the force of gravity changes by 6 times as much. So whatever that force of gravity was before, now because of these changes, it's going to increase that force of gravity by 6 times. Okay. All right, so we have learned 2 ways to calculate the force of gravity. So I'm going to make an illustration here. So here's the Earth. Okay? And here's you standing on the Earth. I'm drawing you in a lot larger scale than reality, but we've learned 2 ways to calculate the force of gravity. One is the force of gravity is equal to mg. And now, Newton's universal law of gravity says that force of gravity is equal to big G times m1 times m2 divided by the distance between the 2 objects squared. Well, here's a cool little math trick that will help us calculate what the acceleration due to gravity is. So on Earth, we know that g, the acceleration due to gravity, is 9.8 meters per second squared. And we're just going to show you how to calculate that, okay, using some math here. So if force of gravity is equal to mg and this force of gravity is equal to all of this, what can you say about these 2 terms? Another way to ask that is that A, if it equals B and B equals C, how does A relate to C? And the answer is A has got to be equal to C. And so these 2 terms here, because they equal the same similar number, they're going to be equal as well. So I'm going to set them equal to each other. So mg is equal to big G times m1 times m2 divided by the distance between them squared. So if we're going to find out what the acceleration due to gravity is on Earth, okay, we're taking the acceleration due to gravity between you and the Earth. So let's call one of the objects u and the other object Earth. Okay, so let's see if this makes sense. The mass of u times g, that's how you would find your force of gravity, is equal to big G times the mass of one of the objects we're going to call u, and the mass of the other object we're calling the mass of the Earth, divided by the distance between u squared. Well, the distance between you and the Earth is essentially the radius of Earth. Okay, so I'm going to put the radius of Earth, but we have to square that number. Okay, now if you can follow me through the math of this, if you have mass of u on the left and mass of u on the right, they will cancel out. So we can cross those out. So here's how you calculate the acceleration due to gravity. Okay, so we've got this equation. G, what's left here, what I'm just doing is simplifying this. G is equal to big G. The mass of u got canceled out, so it's just the mass of the Earth divided by the radius of the Earth squared. Okay, and that will help us calculate what the acceleration due to gravity is. We know that on Earth, it's got to equal 9.8. We know what G is. G is equal to 6.67 e to the minus 11. The only thing that we need is the mass of the Earth and the radius of the Earth. then we can complete this equation and put it in our calculator, and it should equal 9.8. So let's do that. Let me look up what the mass of the Earth is and what the radius of the Earth is. Just give me one moment. Okay, so I just asked Siri what the mass of the Earth is. And so for mass of the Earth, we're going to put in 5.97 e to the 24th kilograms. And the radius of the Earth was 6.37 e to the 6th meters. And then we're going to square it. So I would like you to try that. I know it's not on the guided notes, but try to calculate what g is. So we're going to put 6.67 e to the minus 11th times that by the mass of the Earth, which was 5.97 e to the 24th. And then we're going to divide that by the radius of the Earth, which was 6.37 e to the 6th. But don't forget to square this number. And you should get that g is equal to 9.8, and of course it's meters per second squared. Okay. So I want you to try that. Put it in your calculator and see if you can actually get 9.8 there. But that's kind of a really interesting equation. So as long as we have the mass of the planet and the radius of the planet, we can calculate what g is, the acceleration due to gravity. And of course it's going to change depending on where you're at in the solar system or the universe for that matter. So I've got a practice problem, number 6, is where you're going to do this. Okay? You're going to use this equation right here to solve for the acceleration due to gravity on the Sun, the Earth, the Moon, Mars, and Jupiter. You will need the mass. Well, first of all, you're going to need g. I'm giving you g. It's right here. It's this number. So you're going to put that in for g. Okay? The mass, which is right here, is going to come in right here. And the radius goes in right there, but you got to square it. So I'd like you to take a second. Maybe I'll go through the first one with you. Okay, let's do it. Let's figure out what the acceleration due to gravity is on the Sun. So we know that g is equal to, I'm just going to use this equation right here. Because there's more room, I'm going to do it right here. So big G, which is 6.67 e to the minus 11th, times that by m, the mass of the Sun, is 2 times 10 to the 30th. Divide that by the radius of the Sun, which is 6.96 times 10 to the 8th. But don't forget to square it. Okay, so let me put that in my calculator. 6.67 e to the minus 11 times 2 times 10 to the 30th equals, and then divide it by 6.96 e to the 8th squared. Okay, and here's what I get. The acceleration due to gravity on the Sun would be 275 meters per second squared. That is incredibly large for the acceleration due to gravity. Imagine if you dropped something on the Sun, in 1 second later, it's going to have moved 275 meters. So that thing is, on Earth it's 9.8, so I'll give you that one, 9.8. On the Sun, 275, so there's just an extreme force of gravity, and the acceleration due to gravity is very large. I would like you to plug in the values and figure out what the acceleration due to gravity is on the Moon, Mars, and Jupiter. So please hit pause and try that real fast. Okay, so let's see how you did. Hopefully you went through and solved for those numbers, but I did it as well, and I got 1.6 was the acceleration due to gravity on the Moon, 3.7 on Mars, and 25 on Jupiter. So, kind of interesting. Next time in class we're going to do a lab where you're going to see how far you would be able to jump on the different places in our solar system, on the Sun and then all of the planets. And because the acceleration due to gravity is so much different, depending on where you're at, how far you will jump is drastically different as well. And so it's kind of interesting to see how that changes. But anyway, that's how we calculate the acceleration due to gravity. Okay, let's talk a little bit more about the acceleration due to gravity. On Earth, is it always 9.8? And the answer is no. Why? Because the acceleration due to gravity, g, is equal to g times the mass of Earth divided by the Earth's radius, or the distance between Earth and whatever you're talking about, so Earth's radius squared. So I'm just going to put d squared. But elevation can change, so how far away you are from the center of the Earth changes. So as you can see in Pikes Peak, the largest elevation, it's not 9.8, it's 9.789. Now it's very close to 9.8, but it does change. So it's not always 9.8. So I just thought it was kind of interesting. Okay, so I think I've got one more slide on this video. And here it is. It says, if apples fall to the earth, why doesn't the moon fall into the earth? Okay, so of course if you drop an apple, it's going to hit the earth, but the moon's out there and it feels a force of gravity toward the earth. So how come if the moon feels a force of gravity toward the earth, it doesn't crash into the earth? Okay, that's the question I want you to think about. I've got this YouTube video that will explain it, and so we'll watch it and see if it'll make sense. We'll talk about it after it's done.
Why doesn't the moon fall down?
Actually, the moon is always falling toward the Earth, but it's moving so fast that it will never hit. When we throw an object, like this tennis ball, gravity pulls it down towards the center of the Earth. Even the fastest moving tennis ball will eventually hit the ground. But as objects get farther away and start moving faster, things change. The moon is so far away and moves so fast that down is never in the same direction. Even though it's constantly falling, the moon never hits the Earth. Instead, it falls around the Earth in a continuous circular path. If the moon were moving a lot faster, it would escape Earth's gravity and fly off into space. If the moon were moving more slowly, gravity would pull it down to the Earth. This delicate balance of speed and gravity creates what we call an orbit, where a smaller body circles around a larger one continuously. The moon orbits around the Earth this way, just as Earth and the other planets orbit around the sun. Most man-made satellites orbit the Earth. However, some are launched beyond the Earth's gravity so that they orbit the sun instead. For Ask an Astronomer, I'm Doris Dow of the Soto Science Center.
Okay, so besides having a really nice accent, she did a good job of explaining why the Earth doesn't, or the moon doesn't crash into the Earth. Okay, and the answer is that here's the Earth, and the moon has such a high horizontal velocity that it keeps going around, but gravity pulls it in, so it's just in an orbit. Okay, and she did a great job of explaining that in order to be in an orbit, the object that is orbiting is smaller mass than the object it is orbiting. So the moon has a lot smaller mass than the Earth, and it's constantly falling, but because it's moving so fast, it always misses the Earth when it falls, and so it is always in free fall. But because of its velocity, it always will miss Earth. And so anyway, hopefully that kind of makes sense. I just wanted to review before we end the video what we talked about, okay? So we now know two ways to find the force of gravity. Force of gravity is equal to mg. We've talked about that all year. Now we've got a new equation. Newton's universal law of gravity says that you times it by big G, which is a constant. The mass of one object times the mass of the second object divided by the distance between them squared. Okay, so we can use that equation to find the force of gravity between two objects anywhere in the universe, not only here on Earth. So hopefully that helps. Before we quit the video, you now know enough to do the force of gravity worksheet in your student workbook. So please go there now and complete that. Again, it's called the force of gravity worksheet, and hopefully this helped.